Why are some populations very stable? Why do others, on the other hand, increase quite rapidly? And what makes them come back down? Why don't they just keep increasing to infinity after that? This idea that populations don't grow to infinity and don't necessarily crash to zero has invoked the concept of regulation. That is, that populations have factors that prevent them from getting too big and rescue them when they get too small. This idea of regulation is different than how big is the population. It's really about the controls on the population. So regulation refers to the fact that populations have boundaries, a ceiling and a floor below which they don't occur, that they have a tendency to return to some equilibrium, some average, and that they don't go extinct. They rarely go to infinity, and they rarely go extinct. And when they fit these criteria, populations are thought to be regulated. So the question is this true? Are populations actually regulated? And what are those factors that prevent them from getting too big and rescue them when they get too small? What is it that regulates insect populations? One way to get at this question is to start with relatively simple models. That is, simplified representations of the world that allow you to see what would the behavior of a population be if we make certain assumptions about how populations grow, or how populations are affected by other factors. So we're going to spend the majority of this lesson here breaking down and talking about very simple models. Some of you may have a lot of experience with this, so you could just fast forward through it, culminating with the development of two often used models in insect ecology and in biological control in particular, the Lotka-Volterra model and the Nicholson-Bailey models. And both of these have some interesting features that allow us to kind of explore what is it that affects the growth and dynamics of populations. So let's start here. Let's start with a very simplified breakdown of how might we characterize a population. Well, you can think of a population as a bucket. And in this bucket, there's a certain level. That's the number of individuals that are there. Maybe ping pong balls. Let's imagine each individual is a ping pong ball. We put them into that ping pong ball. And the way we get the level in that bucket to go up is either by taking balls from the outside and putting them in, immigration, or for each one of those little balls to give rise to new balls. They reproduce, there's births. If either of those two things happen, then the level of that bucket is going to go up. In order for the population to decrease, a couple of things can happen. One is those balls might actually leave. There's emigration out of the system. Individuals leave that population and go somewhere else. Or those individuals are eaten or killed or die, or something happens to them. We just make them disappear or destroy the ball or something like that. So the population at one point in time can be predicted for the next point in time if you know something about any one of these four factors, or all four of these four factors. So the population at time t+1 depends on how many are there to start with, how many balls are in your bucket, how many are born, how many die, how many come into the population from the outside, and how many leave the population from the inside. Most of the models that we're going to start with and talk about for this session here simplify the system by not including or not considering emigration and immigration. That is, the population is closed. All of the dynamics can be explained by those things that are happening just by births and deaths within that population.